guys, it's Miss Miklos, and today we're going to be talking about the beginning of chapter 4, which is going to talk about one of my favorite things, trigonometry. And so today's going to be a pretty straightforward, basic introduction. In fact, you guys learned most of this last year in Algebra 2. And so let's get straight into it. Okay, so trigonometry, as we all know, is the study of angles. And if you didn't know, now you know. And just a reminder back to geometry, angles are basically when we have two rays that have a common vertex. And we always like to put our angles in what we call standard position. And that means that the, the initial side is at the positive x-axis. And we have our vertex at the origin. And we call the other side the terminal side. And so if we look over here, just to kind of demonstrate, this would be our initial side. Our vertex is at the origin here. And our other side would be in quadrants 1, 2, 3, or 4, depending on what we were actually doing. And we would call that our terminal side. But this is how we're going to go ahead and draw every single angle for this chapter. I would say the biggest difference between Trig and Algebra 2 and Trig and Pre-Calculus is we really focus on the unit circle. And the unit circle really helps us figure out things in terms of radians. And I know last year we liked degrees. We're used to degrees. It's like our native language. It's English to us. Radians, we know, are equivalent to degrees. Okay, it's just another way of measuring angles. But often, it's like it's a foreign language. So it's like we're speaking Spanish, where often we do better in our heads. If you're in Spanish or French or Latin or German or whatever class you're in, we often try and translate it into English in order for us to understand. We know we are truly fluent in something if I can just think in that other language. So our goal this year is we want to be fluent in radians, and we just want to be able to think in terms of radians. So some things that I just want to talk about. We know this formula C equals 2 pi r. That goes back to geometry. And for our unit circle, it actually might be helpful if I kind of go back to this whole page here. We're going to use a radius of 1. So I substituted 1 in for the radius. We know that the radius around an entire circle is 360 degrees. So this tells us 360 degrees, which is the circumference, is equal to 2 pi. And if I divided both sides by 2, pi becomes 180 degrees. So this is the biggest thing that I'm going to stress to you this chapter. Pi is a semicircle. I know that we're really used to seeing pi and thinking 3.14, so it's going to take a little bit of adjustments for us. Okay, we do say that the unit circle is split into degree increments of 15 degrees, and it's split into radian increments of pi over 12. And so we're going to take a moment here, and it might be a little bit more than a moment, but we're going to focus on just the positive angles and talk about them in terms of both radians and degrees. So the first thing I want to remind us, okay, here's the x-axis and the y-axis, and we call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4, and I know you guys have heard that before. I also want to start in degrees with labeling what we call the quadrantal angles. And all the quadrantals are going to be on the 4 axes. So really 2 axes, I should say, but positive x, positive y, negative x, and negative y. So we would say that this is 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Okay, next thing I want to just remind us of, if I bisect that, it would be 45 degrees, 135 degrees, 225 degrees, and 315 degrees. I forgot over here, just to remind us, that this is also what we would call 360 degrees. The other angles that we use quite a bit are 30 degrees, 60 degrees, 120 degrees, 150 degrees, 210 degrees, 240 degrees, 300 degrees, and 330 degrees. One thing I want to notice every single time I'm using the degree symbol, yep, I'm touching all of them, and that's because we really need to specify something is in degrees or radians. Now, the significance of these 12 angles is those are what we call our special angles, and we will get into those in more depth sometime later this chapter. Our last few, we have 15 degrees, 75 degrees, 105 degrees, 165 degrees, 195 degrees, 255 degrees, 285 degrees, and we lastly have 345 degrees. So I think that we're really familiar with these measurements. This is what I was saying earlier is like our native language. And so I actually want to take a little bit of time now and talk in terms of radians. Okay, when we're talking in terms of radians, the big thing I talked about earlier was the fact that pi represents a semicircle. So we would call this positive x-axis 0. And a semicircle going all the way around would bring us to the negative x-axis, which I'm going to call pi. If I go all the way around again, it would be like 2 semicircles, so we would call it 2 pi. Up top, where we would think of 90 degrees, that's actually half of a semicircle, so I would call it pi over 2. And down below here, this is like 1.5 semicircles, so it would be like 3 pi over 2, because that's like 1.5. I know that a fourth of a semicircle would be pi over 4. 3/4 of a semicircle would be 3 pi over 4. 1 1/4 of a semicircle would be 5 pi over 4. And lastly, 1 3/4 of a semicircle would be 7 pi over 4. So that would be like 1 3/4. Okay, so once again, pi represents a semicircle. Some other ones that we see quite frequently, pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. And you guys may notice a pattern here that everything that has a denominator of 6 is closer to the x-axis. Things that have a denominator of 3 are closer to the y-axis. And later in this chapter, we will learn more similarities between everything that has a denominator of 6, everything that has a denominator of 4, and so forth. Our final ones, we would have pi over 12, 5 pi over 12, 7 pi over 12, 11 pi over 12, 13 pi over 12, 17 pi over 12, 19 pi over 12, and 23 pi over 12. Okay, and I don't want to stress you out and talk about like that we need this memorized by any means, but what we really need to know is what quadrant something is in, and that's going to be a skill that is imperative for us to be successful in this class. So for example, If I give you something like 5 pi over 6, I need to think, what quadrant would 5/6 of a semicircle be in? And I know 5/6 is not quite 1, and it's more than 1/2, so that means it would have to be somewhere in quadrant 2. If I had something like 5 pi over 3, I know that's 1 2/3 of a semicircle, which would bring me into quadrant 4. Okay, so that's what I want to stress to us. It's not necessarily about knowing exactly where it should go. It's all about knowing what quadrant it is in. Okay, just a reminder once again, we call these our quadrantals. Now with our negative angles, okay, we know this is still x and y, and our quadrants are still 1, 2, 3, and 4, and yes, we do use Roman numerals for those. The only difference about a negative angle, and I'm actually going to bring it back to the positive angles here, when we have a positive angle, that always means that we move counterclockwise. So I'm moving counterclockwise, and that's the way at this point in time that we're really used to working with angles. Now with negative angles, that just means that we are moving clockwise. So if I look, okay, here's 0 degrees, negative 90 degrees means I'm moving 90 degrees away from that positive x-axis in a clockwise manner. This would be negative 180 degrees, negative 270 degrees. Okay, and I'm not going to go through and label everything. I think we can figure that out. But the whole idea here is if we have a negative measurement, we need to move in a clockwise manner starting on the positive x-axis. So what you guys may have seen is that we have some angles that are in the same location that we actually give different names to. So coterminal angles have the same standard position. And I often like to think of it as saying same angle, different name. So it's letting us know it's the exact same angle. We just can call it something a little bit different. So some things that we can do if we're working in degrees, I can add or subtract 360 degrees. And the reason why we would use 360 is because that is an entire circle. When we're talking about radians, we would add or subtract 2 pi. Because we've said pi is one semicircle, so 2 pi would be the entire circle. So we're going to go ahead and transition into saying what quadrant is it in. And I know that a lot of you guys will be tempted to go ahead and convert this into degrees, but I'm actually going to go ahead and use radians, and remember that pi, for the millionth time, is a semicircle. So I have to think, what is 1/6 of a semicircle? And if I was thinking about this, 1/6 of a semicircle would be in quadrant 1. So I'm going to go ahead and say quadrant 1. Notice when I drew this, I drew an arrow indicating the direction of the angle. Now, when we're drawing this, honestly, it doesn't really matter how accurate we are. What matters is that we're in the correct quadrant. So our next one, 2 pi over 3. Okay, if I was doing 2/3 of a semicircle, that would take me somewhere into quadrant 2, because I know it's not a full semicircle yet. 3/5 of a semicircle, 3 pi over 5. I know 3/5 is somewhere between 1/2 and 1. Does not matter how accurate I am. Once again, what matters is that I understand that it is in quadrant 2. Okay, 7 pi over 5. I'm going to change this. You guys probably already know this. I hate mixed numbers. I think they're dumb. But I think sometimes when we're talking about things, it's helpful, and this is one of those instances where this is telling me, let me try and go to a different color. There we go. That I'm going to do 1 2/5 of a semicircle. I know 2/5 is a little bit less than 1/2. So I'm going to go ahead and put it in quadrant 3. Now number 5 is kind of tough because this is telling me -3 2/3. So if I'm thinking in terms of graphing this, first of all, I have -3 semicircles. That negative just indicates a direction. With the first 4, notice we automatically went in a counterclockwise direction. In this case, I need to move clockwise. So I'm going to move 1, 2, 3 semicircles would bring me to the negative x-axis. Now from there, 2/3 of a semicircle would bring me somewhere over here. So I'm going to go ahead and draw that, and I notice that it is in quadrant 1. So once again, I cannot stress enough, pi represents a semicircle. Okay, our last one here, this would be like -2 1/4 semicircles. So I'm starting on the positive x-axis, and since it's negative, I'm moving in the clockwise direction. 1, 2, and 1/4 of a semicircle would land me in quadrant 4. You guys may still be wondering, what are radians actually representing other than the fact that Miss Miklos is saying it's a foreign language? And what it really means, it's the measure of the central angle theta that intercepts an arc. It's when it's equal in length to the radius r of the circle. So the measure of the central angle is equal to the radius, okay, which is kind of a weird concept. And to be totally honest, in this course, it doesn't matter that much if we understand all the intricacies of that. But I just want to make sure that we're seeing mathematically why it works. Now, the final thing we're going to talk about here is converting forms. So you guys may recall from Algebra 2 that to convert something from radians into degrees, we can multiply by 180 degrees over pi. And just to remind us why this works, it's because 180 degrees is a semicircle and pi is also a semicircle. So it's really like we're multiplying by 1. If I am multiplying, if I'm trying to turn something from degrees into radians, we would multiply by pi over 180 degrees. So let's go ahead and work on this. Convert from radians into degrees. I'm going to multiply by 180 degrees over pi. I notice my pi's cancel out. Don't put pi in your calculator. It just causes a mess. And I know that 180 degrees divided by 4 is 45 degrees. Notice I am putting a degree symbol on here. To take this a step further, if I had to write a coterminal angle, I could add 360 and I would get 405 degrees. I could subtract 360 and I would get -315 degrees. We could add another multiple of 360 or -360. So I just want to stress to us that all 3 of these are actually representing the same angle. They are coterminal angles. Okay, back to the problem at hand, number 2. I'm multiplying by 180 degrees over pi. I notice the pi's cancel out. And for me, I notice 6 goes into 180 30 times. I'm keeping that degree symbol. So I'm going to say that this is -150 degrees. Now, quite honestly, this is normally more the instance where we use a coterminal angle, just because sometimes working with negative angles throws us off our game. So we know 150 degrees is equivalent to 210 degrees because I'm just adding 360 to that. So when I'm converting from degrees into radians, now I'm multiplying by pi over 180 degrees. So I need to somehow simplify 320 over 180. This is when using our calculator and doing math frac can be extremely helpful. I know that the zeros are going to cancel out. So I have 32 pi over 18. Notice my degrees also cancel out there. I notice that those are both even numbers though, so I can reduce this even further and I could get 16 pi over 9. And I can see I cannot simplify 16 over 9 any further, so 16 pi over 9 would be my final answer. If you are choosing to use your calculator to convert this into a fraction, don't put pi in. We know pi is an irrational number, so it will never convert it into a fraction of integers because that's the definition of a rational number. Last problem of the lecture, I'm multiplying by pi over 180. And so my degree symbols cancel out, and I end up getting negative pi over 12 because 180 divided by 15 is 12. So in this lesson, I know it may seem kind of fragmented and random, but important things for us to know. We need to know how to graph an angle in standard position. We need to understand the correlation between degrees and radians. We need to be able to tell what quadrant something is in. We also need to be able to go ahead and figure out a coterminal angle. All of these pieces are going to be coming together later on in some of our upcoming lectures.